Hello, everyone. Welcome to this lecture today. Today, we're going to continue our journey in the circuit theory of the electrical and electronics. First thing first, we're gonna have to share the screen, and we know that. Okay, and have to do that. What that setup? Which one? Hmm. And okay. Now let's begin our class. From the last lecture, we already know that we talked about the Ohm's law and how it differs from reality and in theory. And we talk about the equivalent passive two-terminal resistor network resistance, equivalent resistance, and how to calculate that. A passive resistor network or resistant network is a combination of the branches contains no power supplies or no sources. This kind of a network is called passive networks. So in our lecture, generally means there's no independent sources, either voltage sources or current sources. So this is what we learned last lecture. How to calculate that? If you want to calculate the resistance, the only thing you have to worry about that is the voltage and the current. Once you know the value of the current or expression of the current and the voltage, you can calculate the resistant equivalent resistance. And from last lecture, we also talked about the series connection of the resistors. We know that all these resistors share a current. So all the current that runs through these resistors are the same one, the very same one. So by applying Kirchhoff's current law, we can acquire the relationship of the voltage and between the voltage and the current of each resistor. And we also know that the total voltage of this series connection of the resistors is equal to the sum of the voltage of the voltage on each resistor. And we also talk about the equivalent resistance. It's very simple. We just add all the resistors resistance together, and the total resistance is the equivalent resistance. So the equivalent resistance equals the sigma of Rk. Rk includes every single resistor that is seriously connected in this branch. And the distribution of the voltage across these series resistors could be calculated by using this kind of formula. It's very simple. So there's no difference from what we have learned in senior high. So this part has no difficulty of learning. So I don't think you can follow this. So this part has no difficulty. And we also talk about the distribution of it and how to calculate the equivalent power on this connection of the series connected resistance. We also know that the proportion between the power on each resistors is proportional to its resistance. So the larger the resistance it has, the larger power it takes. So in this case, we know that it means the stronger one takes a larger piece of cake. Similarly, we talk about the parallel resistors and its distribution of current. If we connected a series of resistors together and we tied one end of them to one point and the other one to the other point, so all these resistors will share the same voltage, and we can apply Kirchhoff's current law at other end of the network or other end of the resistor. So we could achieve the relationship between each other. And we see that the total current equals to the sum of the current on every branch. And so we can similarly calculate the equivalent resistance. So the reverse of the equivalent resistance equals to the sum of the reverse of every resistance on the in this parallel connected resistance network. So if there's only two resistors in this loop, it has this relationship, but you don't have to memorize it. We can deduct it from the definition, and we can deduct it from Kirchhoff's current law very easily. And if we put several resistors in this parallel connection resistor network, also we have the relationship between the equivalent resistance and every single resistance in the parallel network. We also have this reverse sum relationship. The reverse of the equivalent resistance equals to the sum of all the reverse of the resistance on the parallel branches. Or we can change it into the very simpler form. We can replace the reverse of the equivalent, the resistance with the conductance. So the conductance, equivalent conductance equals to the sum of the conductance on every branch. So we have this formula. So so in this case, we know that the truth of the resistance or conductance is at a view. Sometimes we use conductance to replace the reverse of the resistance to make the formula much tidy and less complex. So this is what we learned from last lecture. And we also know that if we have a simplest parallel network, two resistor parallel network, their distribution of the current equals to this formula. So, which means the larger the resistance you have, the smaller current you get, and the larger conductance you have, the larger current you will have. And we also know that the equivalent resistance is always smaller than the resistance of the smallest resistor in the parallel combination. So, which means the total resistance must be less than the smallest resistance on the branch. And we know that the larger the current flows through the smaller resistance. So as water, the current similar as water runs through the dam and the conductive aqueduct. The larger the current flow through the smaller resistance. So in this time, the little one gets the larger piece of cake. So we better memorize the equivalent transformation of the parallel and the series connection of the resistors. But it's very simple, so you don't have to put a lot of energy in it. And the equivalent resistance must exhibit the same current voltage characteristic curve as the original network. If you replace the complex network with a single equivalent resistance. So we have to make sure before the replacement and after the replacement, before and after, the network's current and voltage relationship will not be altered. So there will be a same IV characteristic curve before and after the replacement. So this is what we learned from last lecture. And we did some examples. And we also talk about the power relationships. So we know that the power proportion between each branch equals to the proportion of their conductance on each branch. So the larger the conductance you have on the branch, the larger the current you have on that branch. And the total power equals to the sum of the power on each branch. So we add all the power on each branch, add them together, sum it up, and we will reach the total power we have. So then we talk about the connection form of a series and parallel connection. But sometimes we were dealing with some special type of connection. But we also using the series and parallel connection method to transform into the mode that we recognize. For example, if we have this kind of network connections of resistors, we can transform that into what kind of we can just simplify it into an equivalent resistance, into one resistance. And if we have another example of like this, how can we calculate its equivalent resistance, REQ? Now let's begin the transformation. By using the parallel and series connection of the resistance definition, we can recognize that if two resistor share both of their ends, which means they must be in a parallel form. So in this case, we see that this 3 ohm resistor and this 6 ohm resistor share the same two ends. You see? So we can just transform this into this kind of a stuff. We can move this point to this point because there's only a wire between them. There's no resistance in between. So those two, dot A and dot B, is identical. So they are the same point in this diagram. And this is a 2 ohm, this is a 4 ohm, and we see that we have this 6 ohm, and we have this one. So since the other end of the 4 ohm is attached to the very end of it, so we can just like connect it like this. And we also know that the 3 ohm resistor share both this end with the 6 ohm resistance. So we can see that, right? So we can see that the 3 ohm resistor and the 6 ohm resistor are in a parallel form. And this 4 ohm resistor and the other branch combined with series connection of 2 ohm resistor and the 3 with a combination of parallel connection of 3 and 6 ohm resistor. So 4 ohm resistor is parallel to the whole bunch of this stuff. So you can see. So we can also, to simplify that, we can just make it much more explicit. Like this, we can see that 2 here and 6 here, 3 here. Four here. So 3 ohm and 6 ohm resistor, they are in parallel. And together they are in series connection with this 2 ohm resistor. And all these three made up of one branch. Branch 1 we could call it branch 1, and branch 2. They are in a parallel form. Right? So we can just calculate the equivalent resistance by using the methodology we have proposed and the formula we have proposed in the previous PPT. So this is how we calculated that. You see that 3 and 6, they are in a parallel form. So the total resistance of the combination of 3 and 6 in parallel form is equals to the reverse of 6 and reverse and 3. So we can calculate that A must equals to 2, right? So R equals to 2. Then we can replace this branch 3 and 6 with 2, right? So we rewrite this. This is 2 ohm, and this is 4 ohm resistance. And we can replace the latter one. We replace the 6 and 3 ohm with a 2 ohm resistor. So you can see we replaced this part by this one, 2 ohm resistor. So then we see that those two 2 ohm resistor made up could be transformed into one 4 ohm resistor. So we can see that we can replace it. We can replace those two, and with a 4 ohm resistor. So we can calculate the total equivalent resistance of the combination of 2 parallel 4 ohm resistors. So it's very easy to calculate that. The reverse of the sum of the reverse of quarter plus a quarter. So that must be equal to 2. So that's how we calculate this stuff. So you can see that by applying the replacement of the series connected resistor and parallel connected resistors with the idea of equivalent resistance, we can just simplify this kind of a network into one single resistor. So it's very easy. So this complex network does not exist any longer. It will be changed into one single 2 ohm resistor, and the current and the voltage relationship will not be altered. So that part still remains the same. The second example, we see that if you have this stuff like this, and we want to simplify it, so we have to make clear the relationship between each and every resistor, each and every component in this on each branch. You can see that we have this dot and this dot. Similarly, we have 4 dot, but actually we can see that the first 30 ohm resistor, we call it resistor 1, and the second we call resistor 2, and we can call the third 30 ohm resistor resistor 3. You can see that obviously that the first the resistor 1 and resistor 3, they share the same 2 dots. And we can also see that since the point A and point B is connected by a wire, so which means point A is point B, right? Because there's nothing between it. So we see that and we see the resistor 2 is connected to point B and C, and resistor 1 is connected to point C and A. And since point B is point A, so we can see that also the resistor 2 is connected to point A. So we can say that 1, 2, 3. Those 3 are connected both to connected C, A and C. So And we can also call the first 40 ohm resistor 4, and this one resistor 5. You can see that resistor 4 is connected to point D and B, and the resistor 5 is connected to point D and A. So the left end of them are connected to one single point. The other part of them is connected by a wire, so which means they also connected to the same point. So we just erase this point B, replace it with A. We can see we can see that this point is also point A. So you can see that those three are the same stuff. So it's very simple to calculate the equivalent resistance from this transformation. Do you copy? Do you follow? I think it's not very difficult. We just have to make clear the connection of each component, and we just you can find which points are identical or equivalent to the other points. So in this example, we see that those 2 points A and B, the former B, is actually connected by a wire. So actually, those 2 points are the same point. So first thing first, we calculate the first 2 branch, the parallel connection of the 40 ohm resistor. So since they are in parallel form, so the total branch equivalent resistance equals to this one. The reverse of the sum of the reverse of 40 and plus reverse of 40. So it must equals to 20, right? 20 ohm. So we can replace those two with the 20 ohm stuff. 20 ohm stuff. We replace the 40s, right? And those 30 ohm resistor, we can calculate them. Their equivalent resistance. They're very simple. It's the reverse of the combination of the reverse of 30. Right? And now we can tell that it must equal to 10. So we replace those three with a 10 ohm resistor. So, and we see that the 20 ohm and 10 ohm resistor are in a series connection. So the total equivalent resistance must be equal to 20 plus 10, right? So it must be 30 ohm, right?
Yeah.
So what's your problem?
Teacher, can you again explain this transform?
What?
This part, this transform?
What transform? I already explained it. Which part don't understand?
This part.
You don't understand this part?
This part, the transform. How to again explain this?
What did you did? What did you do for the last 20 minutes?
I show you. Here, Simbat cannot understand this one.
For the last 20 minutes, I tried to explain it to you how to transform it. And all the stuff, I put it on the screen and you don't follow. Which means either you are not very paying too much attention to it, or anyway, how we're gonna finish? We're gonna re explain it. Okay. So we see that the question is only you can understand, or all of you can understand. If all of you can understand, we have to put a lot of time on it. But if only you can understand it, which means you didn't do the last homework, yes, you don't, you didn't re go through the stuff we have learned from last lecture. But anyway, we're gonna do it
it's actually
again.
a little bit difficult. It's all things are same, almost same by so it's
Do you understand the first example? The first example, do you, from last page of PPT, the last one, do you understand?
it's a little bit I understand it, but this one
You don't understand this the second example.
yeah I don't know.
Okay. Just we're gonna kill us some time, but anyway, we're gonna do it again. First thing first, we have to make sure the relationship of every branch, right? The first thing first, we have to make clear the relationship of every branch. So we name the dot. We give each point conjunction point a name. First one we call it A. Second one we call it B. And third one we call it point C. And fourth one we call it point D. Right?
Yeah.
So we can just transform this into this kind of stuff. We see that we'll give the resistors a series of number. First, two, the second, the third, the fourth, and the fifth. Between point A and B, we have resistor 1. And between A and C, we have resistor 2. Between B and D, we have resistor 3. B and D, we have resistor 3. And we also have resistor 5. Right? The copy between this dot and this dot. We also have this branch.
Yeah.
Right? They are connected to the same 2 point, right?
Yeah.
And between D and C, we have resistor 4. Right? And we know that point B and point C, they are connected by wire. There's nothing in between, right? Right? So which means B is C. Because if you connected 2 points by a wire in a circuit, which means those 2 points must be the same. So we can replace all this C point in this connection So we can achieve this relationship between A and B. We replace C with B, right? C, we can change it into B. So we can see that between A and B, we have resistor 1 and 2. And between B and D, we have okay, because there is two direction. So we have 3, 4, 5. Right? Do you copy it?
Yeah.
Yes. Yes. Yes.
So see, this is a point A, and this is point B, and this could cause point C or point B or wherever, because those two dot are the same one, and we can call it call this stuff point D. So we just replace all this stuff. So we can just connect it, point A and B. A and B with numeral n. So those two 40s are in this form. And between B and D, we can just connect 3, 4, 5. Like this, right? So first thing first, to list or name the point, and you write the table that describes the relationship of components between the dots, the point, and we can just find the relationship that we can replace the dot that is actually the same dot, but with different names and numbers. So we can have the funnel table of it, and you can rewrite the network by using the just renewed table, right? Do you copy this time? Could you follow?
Yeah, logic.
So this is how we achieve this stuff. And from this funnel connection, we can see that the resistor 1 and resistor 2, they are in a parallel form. And resistor 3, 4, 5, those three are in a parallel form. So this is how we did it, right? And since we know the in parallel connection, the resistance, the equivalent resistance, point A and point B are A, right? Equals to those two resistors in parallel form. And resistor 1 is 40, resistor 2 is 40. So, okay, don't have any.
I think most of
So we can calculate the value of RAB. So which means RAB is reverse equals to the reverse of first resistor 40 and the reverse of resistor 2. Resistor 2 is 40.
Okay.
So from this we can generate that we reach the result of RAB. RAB must be 20.
20.
Similarly, we apply this strategy to this stuff, right? So we can calculate the replacement resistance by calculating the reverse combination, the reverse of the reverse, the sum of the reverse of those three. So we can reach is equivalent. So RBD is, we could calculate that by using this calculation, right? The reverse equals to reverse, the sum of the reverse must equals to 10.
10, yeah.
So since then we can replace those two with one single resistance and those three with one single resistance. And then we can have this $20 in series connection with a 10 ohm. So the rest is a piece of cake. 20 plus 10 equals to 30. Right?
Yeah.
So in this case, we're using the trick to transform the equivalent complex network into a simplified network. So in this form, we this symbol represents the parallel. So and the plus means they are in series connection. So we replace this stuff by this stuff, right? So 40 parallel to 40, and those three 30s are in parallel with each other, and those two groups are in series connection. So we're using this cross to represent the relationship of series connection with the parallel symbol to represent the parallel connection. Since we have learned in algebraic and senior high school math, we're already very familiar with this symbol, which means two lines are in parallel with each other, right?
Yeah.
So I think you could understand it by now. And we already explained this example twice. I think. Anyway, if you don't understand, we cannot do that again.
Thanks, teacher. We got it. We got it clearly.
Okay.
Thank you.
Let's continue. So this is how we using the trick of transformation between series connection of the resistors and the parallel connection of resistors. That's how we do it. So these principles will remain the same no matter where you are, no matter which part you're living in the world. So this is a universal principles. That's better than religion, because religion is very it's not very universal. No matter what you believe, the scientific laws will not change, right? So That's how it behaves. And we can see that another example, if you want to calculate the current in this example, right? How could we calculate the current in this example? If we want to learn the value of I1, I4, and U4, we see that U4 is the voltage of this resistor, and I1 is the current here. I4 is the current on this branch. So if we want to learn about its value, how could we calculate by using the trick we have learned? And it's simple actually. It's not that difficult. We only one thing is very intriguing is that in China, in our teaching practice, we would like to teach students tricks to solve problems. And in Occidental or the Western world, their lecture are mainly about the principles and the tricks. They do not talk about that too much or to that extent as in China. So no, doesn't matter. We're gonna continue our journey. So let's still we name it. We call this one resistor 1, this one resistor 2, and this one resistor 3, and this one resistor 4, right? And we can
See, total four resistor.
And we can see that have 6, and its value we already see that 2 times R, 2 times R, 2R, 2R, R. That's it. And we first solution we using shunt method. How we gonna solve it like this? It's very simple. We can see that first thing first, we see that resistor 2 and resistor 1, they are in a parallel form. So the current, they are in a parallel form. So resistor 2 must have the same voltage as resistor 1. And since their value of resistance are identical, we can see that their current must be the same, right? And so we can see that the combination of those two equals to I3, right? So I3 must be 2 times of I4, but we notice the difference of the direction. So I4, we call it is going into point A. You can call this point A, and I3 is going to point A also. So their direction must be opposite. So, which means I4 equals the half of I3. So we copy that the first part of this, we copy. I4 equals to negative half of I3. We copy. Could you follow? This one I3, this one I4. And we know that the resistor 2 and resistor 1, their branches are identical in a parallel form. So we can assume that the resistors 2 have the same current as resistor 4, right? And since we using KCL current law, we know that I3 plus I4 in first resistor and plus another I4 in the second one, the resistor 2 loop equals to 0. So I3 equals to 2 times of I4, which means we got this one, right? I4 equals to the negative half of I3. So you copy this part. So let's take a 10 minutes break before we continue.
Okay, 老师。
So from the first lesson, we have already learned about how to solve this stuff, and we already calculate the very last part of this connection. So we from the analyzation we have before, we have reached the conclusion that I4 equals to negative half of I3. So let's continue. And since resistor 1 and resistor 2, they are in a parallel form. So and their value of resistance are identical. So we can replace this branch of 2 by using one single resistance. So we call it R1 and R2. So its reverse equals to the reverse of the first resistor 1 to R and plus I to R, resistor 2. Right? So we can replace these two resistors with one single one resistor. That is, we can see that from this solution we can reach the conclusion that R1 and R equals to R. So we can replace those two branches with one single resistor. So with the value of this one. So we cut those two off. And add another one. This one is R1 and R. R2 1 and 2. Its value is R. And we can see that it's in series connection with the resistor 5. So the resistance between point B and point C, we have two branches. the resistor 3 branches and the resistor 5, and we can call this one resistor 7 branch. So between point B and point C, between those 2 points, we have a resistor 3 and resistor 5 plus resistor 7. And resistor 3 has a value of 2R. And resistor 5 is R. And resistor 7 is R. So then we will reach another parallel to R network. Right? Do we copy? So we can replace this part. Oh, I don't think you quite follow. Still, you can see that anyway, we're gonna don't have enough space. Okay. So between point B and C, we have a resistor 3 and resistor 5 and 7 in series connection. And this branch, the left branch, this branch has a value of 2R. The resistor 3 branch has a value of 2R. So those two branch resistor 3 and resistor 5 and 7, they have the same value, 2R, 2 times R. And they share the same. They share the same voltage, right? And the current that runs through this branch, the 5-7 branch, is S3, which means it also the resistor 3 branch must have an equal current to branch 5 and 7, right? We copy.
Yes, teacher.
And we know that I2, I3, and another I3, they come into one junction point B. So for B, point B, we apply KCL laws. We could reach that I2 flows into the point B, and I3 flows out, and another I3 flows out. They must be 0. Then we can have the conclusion that I3 equals to half of I2, right? Do we copy? Do we copy this time?
Yes, Lordship.
So this time we can see that from point E and F, I2 will work through. We can replace this, we can transform this circuit into this new form, right? 12 volt. And this one is 2R. And this one is R. This one is 2R. This one is R. Six, 3, 5, 7, and this R, 2R, and this one is 2R. Similarly, we have this one, B and D, B and C. We have the conclusion that those two make a 2R resistor, and the other branch, resistor 3 branch, is 2R. So we have the conclusion that the I3 equals to half of I2, and this one is I2, right? And we can see from the calculation, we can see that by using the transformation of a parallel resistors, we see that still we have two branches of a value of 2R resistors in a parallel form. So together it could be changed into one single resistor, right? So we replace those three, 5, 7, and 3. 5, 7, and 3 can be replaced. So those 3 can be replaced with one single resistor. We replace with it by a resistor 8, and its value could be calculated as R, similar to the first 3 stars. And we see that resistor 6 is R. So resistor 6 has a value of R. Then we have two branches, right? The first one is I1 branch. I1 flows into point E, right? And still we can see that since this branch, the right branch, and the resistor 4 branch, they are in a parallel form of connection, and their value are both 2R. So which means their current must be identical. So the resistor 4 branch must have the same value of current as the resistor 6 and 8 branch. So we can apply this to point E with KCL. I1 minus 2I2 equals to 0, which means I2 equals to half I1. Right? Do we copy? Could you follow? So to this part, we reach the relationship. What? What? So we have this relationship of I3 equals to half of I2. I2 equals to half of I1. So I1 equals to 2I2 equals to 2 times 2I3 equals to 2 times 2 times 2 times negative 2 times of I4. So that will give us a that gives us a that's a bit annoying. Okay. Already we have the relationship between I1, I2, I3, and I4. So we don't have to leave these marks on the screen any longer. So we have the relationship between the current. I4 equals to the negative 2 half of I3 to half of a quarter of negative I2 and 1/8 of negative 1 I1. And we know that the combined the resistance we can calculate by using this the method we have before. So we have 12 total equivalent resistance of R and a total voltage of 12 volt by using the transformation we have mentioned before. So we can calculate I4. Now we know I4, the value of I4, so we can deduct it. And we know that the relationship between U4 and I4. So U4 could be calculated is 3 volt. And the result must contain R, no, because if you want to calculate the current, you have to using the Volta's law or Ohm's law, both are right. So so this is I1, I4, I3. This is the first method we have to calculate the wanted I1, I4, U4 for the current and voltage. And we also have another trick to do it. We could do it by using the partial pressure method. Still, you can see that it's same stuff, the same. We know that by using the transformation of parallel to series resistors. Before we know that still we can see that U4 equals to half of U2, right? Because those two are in a parallel form. So see U1, U resistor 1, 2, 3, 4, 5, 6. You can rename it like this. And we know that resistor 1 is parallel to resistor 2. And series connected with resistor 5. And the value between the resistors value between point A and point B on the right branch are A and B branch value equivalent resistance could be, right? On the right branch, we can see that is R. This is 2R parallel 2R plus 1R equals to 2R. So we can see that U4 therefore equals to half of this is the value between we can call this E and F, the point E and F. So U4, this one is U4. And 1, 2 in series connection with 5. So, and they have the same value. Those two branch made up one equivalent of resistor of R. So it means U4 is the value, half of the value of U2. U2 is total value between A and B, and those two are in a parallel form. Similarly, we can calculate that again. We know that this branch, the branch on this side, the resistance on this side, we can calculate, and by using the method we mentioned before, we can see that is 2R. So all those branches have the same value of U1, and therefore U2 is half of the value of U1. So we can calculate like this. Still, both methods requires us to do this transformation of the network of resistance. We try to simplify it by using the parallel to series to parallel calculation of the resistors. So in this method, we calculate the value on the branches, and we calculate step by step one loop to another, so we can reach the relationship between the between each 2 points A, B, C, D, E, F. For example, like this one, we can call this point D and point C. So could you follow this? Do you understand?
Yes, teacher.
We're doing the same stuff as in the first method. First method, we calculate the current. The second method, we calculate the voltage. But both using the parallel connection to series connection transformation by calculate the equivalent resistance over and over again. So we reach the relationship between each 2 points of the voltage between each 2 points. So we can reach this conclusion that U4 equals to the quarter of U1. And since U1 is in parallel form with the ideal voltage source of 2 which of with value of 12 volt. So U1 is 12, and therefore U4 is correlated with 3. So we can calculate I4, and we know that I1 is 2 times of I2. I1 is 2 times of I2. Is 2 times of I3. And I3 is 4 times of I3. And it's 8 times of I4. But a different direction, opposite direction. So in this time, still by using the transformation of the resistor network with the parallel connection and the series connection method, we can calculate the relationship between the points, all the points on each branch of their and calculate the voltage on each branch. So this is how we do this example, right? So the main point is still by simplify the circuit by using the method of the relationship between of a parallel and the series connection. This is what this example is about. So still, we can introduce you to another example. We would calculate the incoming resistance of RAB at in a circuit. So see, since we have a two-terminal network like this, and we would like to know the equivalent resistance RAB from those the point A and point B. So we can replace those two with a single RAB. We can just cut them off, and we replace it with a single resistor RAB. So how could we calculate that? So if you want to know the resistance equals to voltage over current. In this circuit, we already know the current is I, which already know that. So we would like to know the value between A and B, UAB, right? So if we could calculate UAB and put UAB over the current, then we reach the final resistant equivalent resistance, right? So we can just assume, right? Assume that the voltage between point A and point B is U, and we know that also the voltage on resistor R is still U, because those two branches are in a parallel connection form. So, and the current that runs through the resistor equals to I minus beta I. Beta I is in this branch. By using KCL, we know that the current that flows through resistor R equals to I minus beta I, and we can replace it into, we can reduce it into this form. So U equals to 1 minus beta times I, the product of I and R. So we can see that RAB is equals to U over I. U is this stuff. I we have, so we can just reduce the current I, then reach the equivalent RAB. So this is how we calculate the equivalent incoming resistance RAB. But there's some space for discussion, right? Let's talk about the value of beta. So if we have a beta that is has a value that is smaller than 1, and so then we have the value of RAB is positive, a positive resistance. So this two-terminal network works like a passive resistance network. But if beta is larger than 1, so then we have a negative resistance, equivalent resistance, RAB. So, what is that? What does that mean? Have you ever seen any negative resistance? Nope. But it will have the effect of a negative resistance since we have a source here. So if beta is larger than 1, which means that this network is not totally passive. It's not it has power source. So the actual power comes from this controlled current source. So this is how the situation changes according to the value of beta. So could be beta B larger than 1? Could. It definitely could. So in reality, if we encounter this kind of a circumstance, we better understand that there must be some kind of a power supply in it. Otherwise, it will not provide you a negative resistance. So this is what this example tells us. So we can see that from the current voltage characteristic curve, we see if we have a beta with less than 1, we will have a normal positive resistance. The total network works like a resistor. And if you have a beta of value larger than 1, and then we have a negative resistance. So then this network works like a source or battery. It provides you with power. It provides you power. Now let's talk about some kind of equivalent transformation in another kind of connection forms. So if you have a network which has 3 terminals outside, right? So it's like just like in our plugs. You see, we have plugs with 2 terminals and plugs with 3 terminals, like that. You can imagine it like that, but it's not 100% identical. But it helps you to better understand it. So if you have a 3 terminal source network without any independent source inside, so there's no independent source inside. So we call it three-terminal resistance or resistor passive network. And there are two types of this kind of three-terminal passive network. One is called the delta-shaped network. You can also call it a piston network. The other one, we call it Y-shaped network. So in those two networks, we both have three ports. You can see that the red dot stuff is could like this one, 2, 3, or 3. And this one, the Y-shaped stuff, is also have 3 output terminals. So those two are both three-terminal passive networks. But obviously, their inner construction relationship is different. So they have a different inner shape and relationship. So let's talk about how could we transform one of these to the other and vice versa. This is the main topic that we're gonna talk about in this lecture. So when we talk about the Y-shape or the tree-shaped network, it could be right like this, Y-shape. Obviously, you see it directly, but it could be it could look like this, or T-shape. Both are right. So it's very important to tell that, so discover this kind of a connection in the network. So once we have seen this kind of stuff in the network, it helps a lot to analyze it. So since it's very typical connection or typical structure in the circuit. So it's very common and very useful to transform this kind of a connection into another. So those two could transform to each other. Also, we can see that the delta shape or pi shape network, we can see that this is a typical delta shape network. It forms a triangle, and the other one, this one, forms the shape of pi. But theoretically, those two are the same stuff, because we can see that this point we call it point A, and this point B, this point they are connected with wires, so they are basically the same point. So we can replace it. We can rename it A, and we can see that this point A and this point B, they are connected by a wire. So point A is point B. So although they look different, but those two are identical, and the upper two are identical to each other. So this is two typical three-dimensional network inner structure. So, but in reality, could the structure inside three-terminal network could be much complex. But we're still using our method to analyze it step by step. So first we talk about we're going to talk about the transformation of the Y or piston shape piston network. those two kind of circuit could be transformed to each other through the equivalent method. But under certain prepositions, so which means it requires them have the relationship, special relationship between their the value of their resistance. So what is the equivalent conditions of the T and the Y shape transformation? We can deduct it from the very basis of Kirchhoff's law. Kirchhoff's laws, we can see that since we have a point 1, point 2, and point 3, so these three are the terminals, three terminals, and this Y-shape network, we also have 3 points, 3 terminals, 1, 2, 3. So the equivalent conditions is from the outside view, the current identical from each terminal. So I1 delt equals to I1 Y, I2 delt is to I2 Y, and I3 delt equals to I3 Y. So the current on those 3 branches must be equal. But the inside it could be different, but we don't care. We just have to make sure from the outside point of view perspective, we can assure that the current that flows through each and every 3 of the terminals of the network are identical. That is equivalent conditions. And the other condition is the voltage between each pair of those 3 terminals must be equal. So the voltage between point 1 and point 2 in the delt shape, we call it U12 delt. The other one is U12Y. So this is the voltage between point 1 and point 2. So U23 delt equals to U23Y, and U31 U31 delt equals to U31Y. This is the equivalent condition. So from the outside view, the current flows through the 3 terminals are identical in the equivalent transformation, and the voltage between any 2 terminals of the 3 terminal network must be equal. So which means from the outside view, the inner equivalent resistance between any 2 terminals must remain the same before and after the transformation. So let's calculate it by using Kirchhoff's current law. So first thing we talk about the delt connection. We know that the current I1 delt equals to the current U12 delt over R12 and U31 delt over R31. So by using Kirchhoff's current law, we see from the point to point A that the current flows in must equal to current flows out. And we see that already we assume that the direction of U12 is positive, the higher on the upper side, and U31 delta is negative on the upper hand. So this one take a negative symbol, and the first part is positive. Similarly, you can see we can write the relationship between the current through 3 terminals and the voltage between 2 terminals. So we can have this set of equations to describe this kind of a relationship. Similarly, we can do it to the Y-shaped network. But this time, since it only has 3 inner current, so we have we could use the current to describe the voltage. So the voltage between point 1 and point 2, we define it as U12Y. And we assume the higher up end of it is positive. So we can calculate by using the KVL. Voltage law. Similarly, we can reach the other 2 terminal voltage. And we also know that to the center point, the KCL law must stand. So all 3 current add up together at any moment must equal to 0. So this is the relationship between the terminal current and the voltage in the Y-shaped networks. So we can compare those 2 set of equations, and we can calculate their relationship, since we assume that I1 delta equals to I1y, while U12y equals to U12 delta. So if we replace the voltage of U12y with U12 delta, theoretically speaking, that the outcome will not be changed. So from the second set of equations, we have the relationship between the current and the voltage like this. And from the first set of equation, we have this relationship between the current and the voltage is like this. So we can compare those 2 together. So the first part must equal to the first part. Is below, and the latter part must equal to this part, and also with the bunch of stuff below. So we can compare 3 to 1, and we can reach the condition that allows one well-shaped circuit to delta-shaped connection form. So we can reach the conclusion like this. So so much for this morning. Let's continue our journey in the afternoon. Thank you for watching.
Thank you, Laushi.